This is video 14 of the GCSE Physics video series all about light. Now, it's quite a short video, but there's an awful lot in it, and there's a lot of this stuff which is for those who study physics GCSE triple science only, not the double science award, but I'll cover it all anyway. So we are looking at optics, light and optics, how light interacts with surfaces, whether they're flat surfaces, what we call plane surfaces, or curved surfaces. And we've already met some of these ideas already. We're going to start by looking at light reflection. Now, the law of reflection, this one here, for specular reflections, the angle of reflection is equal to the angle of incidence. And that is what we can see in diagram B here, as the ray of light is incident upon the mirror surface, the reflecting surface. If we were to draw a line at the point where the ray is incident on the surface, 90 degrees to the surface, we call that the normal, and measure the angle between the incident ray and that normal, that would be called the angle of incidence, and it would be identical to the angle of reflection. That's the angle measured between that normal and the reflected ray. Now, I've mentioned that is for specular reflections. Mirrors produce specular reflections. This is the idea that parallel rays are travelling in the same direction, and rough surfaces produce diffuse... accidentally pressed the wrong button. And rough surfaces produce diffuse reflections. Reflection's a little bit more complicated than that. I did a video just a little while ago where I went into a bit more detail about some interesting reflection mechanisms, what the physics of reflections is. It caused quite a bit of commotion on the comments section with people saying that they disagreed, and then reading around and realizing that actually they did agree with me and all that sort of thing. There's no point putting the video there, it's going to cause confusion. I'll have to have a little think about how better to explain what I was trying to say. So the picture we're presenting for reflection here, this is a cartoon. It's a simplification. It's a bit more advanced than what we're showing here. What we'll say at GCSE level is that diffuse reflections are a consequence of having a rough surface. The angle of incidence still equals the angle of reflection for each ray, but each ray, if you have all these parallel rays coming in, they're going to strike a different part of the surface, so the surface angle is different to the ray depending on which ray you're looking at, and so all the reflected rays come off in different directions, and we have a diffuse reflection. That does happen, but the main cause of diffuse reflections isn't reflection from the surface, it's penetration into the surface and then scattering. But we'll not go into that in GCSE level. Can't help myself. So specular reflection and diffuse reflections, you do need to know those two. And the law of reflection is easy to see it apply in specular reflections. Angle of incidence, I've said here, between the angle between the reflected ray and the normal. Angle of incidence, angle of incidence is between the incident ray and the normal. Angle of reflection between the reflected ray and the normal. I had a horrible feeling I'd got it wrong on the board then, because I seemed to say it wrong. But no, it's right there. Normal, a line that's 90 degrees to the surface, fine. So there are some other technical words relating to reflection of light. The idea of the formation of an image. So the image, or any image, is a point where you can consider rays diverging from it. Now, it might be that the rays do actually pass through that point, in which case we call it a real image, or it might be that the rays don't actually pass through that point, and this is what happens with mirrors, where you get a virtual image, a point where it looks like the rays are coming away from that particular point, but the rays don't actually pass through that point. So virtual images, you can't project them on a screen, and if you view the image from different angles, it appears to be different. Now, there's a diagram on the right here. This is a hand-drawn diagram on a piece of paper that I drew and then scanned. Actually, I think this was on the board with a whiteboard pen, and I was so happy with it, I took a photograph of it and then, adjusted the image so that it was black and white and so on and so on. It's good to construct this diagram together in real time. I know it's a slight deviation because really all I wanted to do in this video series is present these presentations in a way that you could follow in order to help you with note-taking and summarizing. But actually, this is quite important. So let's have a look at the case I've just shown you, where we have a mirror, which hopefully OneNote will know that I was trying to draw a straight line. Come on, OneNote, you're cleverer than that. Delete that. Let's draw. Yes, there we go. There is my mirrored surface. And then let's consider an object, which I'll draw in. Yeah, okay. Progressively select a symbol. Oh, what's it talking about? Right, so let's now select a. Let's do it in. Yeah, let's do it in green. Let's place an object. And I'm going to place an object here. Label it object. This is the thing, object. This is the thing that is radiating light. It could be reflecting it, so it's a secondary light source. It could actually be a lamp or a light bulb and producing its own light, a primary light source. I don't know, it doesn't matter. That is the thing. If I'm looking in a mirror, that's my face. This is the object. Now, what I do know is that the rays are going to be emerging from that object in all directions. So I could just pick two rays. I'm going to pick this ray, just like this, and I'm going to pick this ray. I'm just picking two arbitrary rays. It doesn't matter which rays I pick, those are the rays I've chosen. Now, for each of those rays, when they are incident upon the surface, there is a normal. And so I can draw that normal as being a line 90 degrees to the surface, just like that. Now, usually we would represent the normal as being a dotted line. So let us turn this into, no, wrong one, point eraser. Oh, it's too thick. Let's turn this into a dotted line, the age-old method of rubbing out part of the line. There we are. So those are the normals. Now, the angle of incident is equal to the angle of reflection. So let me get a ruler out. Draw ruler. And let's get some angles measured. So here's my ruler, or something close to a ruler. Let's rotate this around. The normal there is, well, I'd rather have the normal at 0 degrees so I could get a... Why am I not able to get it exactly on 90? Never mind. It calls that 90 degrees, which is a bit naff. I'd rather that be 0 degrees. But we're clever enough at working with angles that we'll be able to figure it out. Let's start with this one. Here, we're now going to rotate the ruler around. So when it says 80, that's 10 degrees. When it says 70, that's 20 degrees. Yes, 80 is 10, 70 is 20. Now that's 30 degrees. It's more than 30 degrees. More than 40 degrees, more than 50 degrees, carry on, more than, oh, it's nearly 60 degrees, let's go a bit further, oh. It's basically 61 degrees, although I can't have half degrees on this particular protractor. There we are, there's basically 61 degrees. 61 plus 29 is 90, so that works out. So that angle there is 61 degrees. I could even label it 61 degrees. Measured with my protractor, which is built into my ruler on this, that's 61 degrees. Now what that means is I need to draw my reflected ray 61 degrees. So let's go around to 90 again. And let's draw my reflected ray 61 degrees as well, which should be there. Oh, bum, I missed it. Let's go back one there. That's 61 degrees as well. Remember, we're measuring from the normal, so I'm a little bit irritated with myself for drawing the mirror horizontally, so I've got to mess around with all the angles, but that is 61 degrees. Get a protractor on the screen if you don't believe me and measure it yourself. 61 degrees. So this ray I'm now drawing I will now be drawing, that is the reflected ray where the angle of reflection is equal to the angle of incidence. Let's draw our arrows. We always draw our arrows, and this is 61 degrees. Well, that's fine, but what I'm saying is if I were over here, so I'm going to represent myself by drawing an eye. This is my eye looking along this ray. What would I see? Well, if I look along this ray, I would see the object with that eye somewhere along this ray. I don't know where, but somewhere along that ray. So what I can do is I can project this ray back. I'm going to use a different colour for that, just so we know that what I'm drawing is a projected ray. It's not a real ray. The one in green is a virtual ray, which extends into the mirror. Now, obviously, the light doesn't actually come along this green path because there's a mirror in the way. The light doesn't penetrate through the mirror. But to my eye, it looks like the object is somewhere along that line. So my eye, my brain, thinks the object is somewhere along this green, around here somewhere. Now, luckily, I have two eyes, which means I have binocular vision, which means I can measure, I can see depth. So let's do the same thing now. We'll do the same thing now with the other ray. Because I have binocular vision, I can use the other one. So that says 51 degrees. It's not 51 degrees because we measure from the normal, and this is dopey because I can't change it, so it's 0 degrees is vertical. So 90, subtract 51, 39. So that's 39 degrees angle of incidence for this second ray. Let's label it 39 degrees. And so the reflected ray, this is the angle of, this is the incident ray, the reflected ray will also be at 39 degrees. So let's rotate this around. There it is, 39 degrees. And I can place my ruler 39 degrees, just like that. And I can draw, come on, there it is. And I can draw my reflected ray. And the light is actually following those blue paths. So that is also 39 degrees. And if I were to place my eye here, my second eye, I would see that the ray is emerging from the mirror in this direction. And my brain doesn't know there's a mirror there. So somewhere further back is where this eye will think that the light originated. Just like that. So those green rays are virtual rays. The light doesn't go there. My brain is not clever enough to know that. Now, if you look, I haven't quite drawn them in the right place. I could possibly click them and nudge them, but I'm not going to bother with that. I just don't think they... Well, maybe I should. Oh, no. It doesn't quite work that way. I'm not going to try and nudge them all around. It's more effort than it's worth. You can see how the diagram is constructed. Now, the point these both eyes agree is here. So that is the virtual, because the light doesn't actually go there, the virtual image. That is the image of the object. The image. So I can label that as such. I'm going to do a circle instead of an X, and I'm just going to label that image. There was something that was doing the rounds on social media, I think it was last year, might be the year before, all the years merge into one now for me, I'm at that age. But there was something that was doing the rounds on social media where a lot of people with a lack of physics education were placing an object against a mirror with something in between the mirror and the object, maybe a book or a pack of playing cards or something. And they were saying, well, how can the mirror know that there should be an image there when the object is not seen by the mirror because there's something blocking it? Well, it's for this reason. Look at the rays. The rays are reflected. When you look at the image, you're looking at this part of the mirror. It's just optics. I don't know what to tell you. That's how geometry works. It's not a difficult concept. Anyway, A couple of interesting features from this diagram. The first interesting feature, and let's see how accurately I've drawn the diagram, is that the image and the object, yes, good. When you connect the image to the object with a line, I'm going to use red for this one, that line will pass through the mirror normally, so at 90 degrees. That's just the way it is. The image is always going to appear normal to the object, or exactly the opposite of the object. And what else can we do? Well, I can get my ruler out and I can do some measurements. So let's measure on my notches on my ruler. This is I think the big ones are supposed to be centimeters. So 1, 2, 3, 3.2, near enough 3 point, a little bit more than 3.1. Let's call it 3.2. Ruler's still there. 3.2 centimeters, or whatever the unit is. If I do the same thing from the mirror to the object, 1, 2, 3 point, just a little bit more than 3.2, 3.1 and a bit, so 3.2 centimeters. It's the same distance for both. So the distance from the image to the mirror is the same as the distance from the object to the mirror. Now this can be really helpful, because if you ever have to construct this ray diagram for reflection, and you might have to, then you know already where the image is going to form. So you can actually cheat a little bit by drawing the object, drawing the image. You know it's the same distance from the mirror as the object is, and you know that the line connecting the object to the image will pass through the mirror normally. And then once you've got the image drawn, you could just draw these rays, green and blue all in one. Don't bother using colour. Your examiner will mark a black and white photocopy, digital scan, so don't bother with using colour pens. But here we go. So once you've got those rays, you can now connect the point where they connect to the mirror to the object, and you've now constructed the diagram in reverse, but it will definitely be correct. I always recommend my students try and draw the diagram correctly first, the way I did it here, and then they can see why you can cheat a little bit and construct it in reverse. First of all, draw the image, and then everything is right afterwards. So I'll leave that there. In fact, no, I will scroll down a bit, because we're not going to need that again. That is a ray diagram. So where's my PowerPoint? There it is. That is a ray diagram. That's the diagram you can see here on the right for a plane mirror reflection. We might also have to draw a diagram showing reflection from a plane mirror using wave fronts. Remember the wave fronts were defined in video 12? Well, these red lines here represent the wave fronts. That is your reflection diagram done. Not a lot more needs to be said about that. Just learn that diagram. Remember, the waves are always traveling in a direction perpendicular to the wave fronts. Okay, so that was lesson number 84. This is lesson 85, refraction of light. We've looked at reflection, now we're looking at refraction. Now, we saw refraction in the context of waves in general before, so we've already seen this diagram on the bottom right here. The other diagrams I think are very pretty, are very interesting. So this diagram on the top right is a simulation of a beam of light incident upon our surface. And you can see that when this beam of light is incident on this surface, the beam is refracted so that the angle of refraction is smaller than the angle of incidence. Here the angle of incidence is measured to the normal, as always, as being nearly 51 degrees, and yet it's nearly 27 degrees for the angle of refraction. It's a smaller angle, and that's because the second medium, this one down here, is more optically dense. So light goes slower in the lower medium than it does in the higher medium. Well, using that same idea that the lower medium is more optically dense than the top medium, what if light was travelling in the other direction? So you can see this ray here, the angle of incidence is pretty much 0, it's a little bit, maybe it's 1 degree or something, and the angle of refraction, well, we're refracting into the lower density medium, not a big deal, we don't have very much refraction. As the angle of incidence increases, remember the angle of incidence is the angle between the ray and the normal to the surface, you can see the angle of refraction is larger than the angle of incidence. We are refracting away from the normal, and that is because we are moving, our light is going from a high optical density to a low optical density medium. In other words, the light is going slower in the first medium, the lower one, than it is in the second medium, the higher one. So as the light speeds up, it refracts away from the normal. Our light can't go faster than 300 million meters per second, which is the speed light travels in a vacuum. But in more dense media, light is slowed, more optically dense media, light is slowed down. And the more optically dense the media is, the slower the light goes. What's interesting with this diagram is you can see when the angle of incidence is too large, it actually isn't possible to get refraction, because as the angle of refraction increases, it's increasing more than the associated angle of incidence is. And so there is an angle of refraction of 90 degrees and an angle of incidence corresponding to that, which is less than 90 degrees. Which means that we could continue to increase the angle of incidence further, but the angle of refraction cannot be greater than 90 degrees, because when you are greater than 90 degrees, your ray is remaining in the more dense medium. Well, that means that we have reflection, and the law of reflection says that the angle of incidence is always equal to the angle of reflection. So you just suddenly skip bing and get rays down here. This is called total internal reflection, and it does appear on IGCSEs, but not on the AQA GCSE. Also on the IGCSE is the equation for Snell's law. I do a derivation for it in a video somewhere, probably my A-level video, but Snell's law, the idea that the refractive index of one medium multiplied by the sine of the angle between the ray and the normal in that medium is equal to the refractive index of the second medium multiplied by the sine of the angle between the ray and the normal in the second medium. Now, that is not always written that way. Sometimes, well, usually one of the media is assumed to be air, where n for that medium is 1, so we just ignore it. We end up with n equals sine I over sine r, or something like that. But that's not really general enough, and I don't like teaching that equation because it's not general enough. Why can't I bring open my thing to erase that ink? There it is. Erase all ink on the slide. Good. Right, now we haven't talked about any of the other stuff on this slide. So, refraction, change in direction of the wave due to changing speed as it passes from one medium to another. The reason that happens, or at least the reason we're telling you that happens at the moment, remember this is a cartoon, it's just to give you a flavour. When we do A-level, we'll teach it properly. But as this wave front is incident upon the medium boundary, part of it ends up going slower. But the wave fronts must still connect across the boundary. Why is that? Because the frequency in each media must be the same. The same number of waves per second are incident upon the top surface of the boundary as pass through and into the second medium from that boundary. So we don't lose waves, we don't gain waves. So we have this continuous continuous wave front. Well, it is a continuous ray as well, but a continuous wavefront that just changes direction. And it has to change direction because if the frequency is the same, but the wave goes slower, then you must have a smaller wavelength. If f is fixed and v goes down, lambda must go down, which is what you can see here. Wavelength is a distance between adjacent wave fronts, and that is clearly reduced. It's reduced because the wave speed is reduced. Then the only way to have wave fronts that are closer together but still connected to the wave fronts in the first medium is to have the wave fronts change direction. In a GCSE exam, you'd get marks and you'd have to say that part of the wavefront that's incident on the boundary first slows down first, and the other part of that wavefront doesn't become incident on the boundary until later on, so slows down later, and that's what causes the wavefronts to change their direction. It's not a full story, of course, and the reason why this happens is much more interesting. But but we're just having a geometric look, a look at the shapes of things. So light slows down, we've covered that. Wavefronts connect across the boundary. Frequency in each medium is the same. Wave speed to reduce. Frequency stays the same. Wavelength must reduce. This is all just the stuff I've already said. And then a reminder that when you move into a medium of higher optical density, light slows down, so you refract towards the normal, and vice versa. Glass has a higher optical density than water. Water has a higher optical density than air. There are useful mnemonics you can use for this sort of stuff. The reason why I keep emphasizing optical density is because things like turpentine is where it gets weird. Some substances have, compared to, I don't know if it's water and turpentine or what, I can't remember, but you can take two substances where the optical density of one is higher than the other, but the mass density of the other is higher than the first. So optical density and mass density are very often similar, higher mass density, higher optical density, but not always. So just be a little bit careful. Don't assume more dense, more optically dense light goes slower. Unless if you get not given enough information, you're going to have to make that assumption, but it's not always true. So that's refraction of light covered. Lesson 86 next. In lesson 86, we're looking at light and colour. And this is a complicated subject for students to grasp. I need to do it practically in my lessons. I get big projectors out to project up things on the wall to help students. This is just an exercise in knowing some colours, though, because we're just making notes from this stuff, and maybe it's acting as revision aid. So you probably know this stuff already. Primary colours, red, blue, green. They are the primary colours of light. We're not saying the art department is wrong. The primary colours of paint is red, blue, and yellow. Are red, blue, and yellow. They are the primary colours of light. The primary colours of paint are red, blue, and yellow. The primary colours of light are red, blue, and green. Just make your peace with that. We can demonstrate it. Secondary colours. These colours only really exist in our eye. You can get similar, some of them, like yellow and cyan, do lie along the electromagnetic spectrum, but some of them, like magenta, doesn't lie on the electromagnetic spectrum. Magenta is a colour that your brain makes up. So these are secondary colours. Now, if I were to take a blue light source and shine it on a white wall, and that's the only light source around, the white wall will look blue. If I were to take a green light source, shine it on a white wall, the wall will look green. A red light source, shine it on a white wall, the wall will look red. If I were to take a green and a blue light source and shine them both in the same place on a white wall, it will look cyan. Well, it depends on the relative brightness of each. It might not be a true cyan, it might be somewhere else on the colour spectrum, but it's going to have that light blue sort of look. And students are often okay with that one. They're usually fine with the idea of blue light and red light incident on the same place on the wall. It looks magenta. Red paint and blue paint, mix them together, you get purple paint, and magenta looks purple. So, yeah, no problem. Blue and green making a lighter blue, well, I suppose we can see that's a possibility. Blue and green makes a sort of turquoise, and cyan looks kind of turquoise-ish, so maybe. But the one that really messes with students' heads, and they gasp when they see it in the lab, is green light and red light incident on the same place on a white wall will appear yellow. Now that is a fact. I can demonstrate it. It is true. I'm not making this up. Yellow light, as produced in this way, what we see as yellow is the mixture of green light and red light. Now, it is possible to get a true yellow light. There are yellow emitters of light. Sodium lamps emit yellow light, for example. True yellow light. But the reason why we see the colours in the way we do is because of the receptors in our eyes. So we've got a few receptors in our eyes. We've got our rods. They are sensitive mainly to green light, but they're quite a broad spectrum of colours. But the rods are really sensitive to light and dark, to bright and dim light, and they're much more sensitive to dim light than the cones are in our eyes. So your brain gets the signal from the rods, and it just uses that to work out how bright or dark something is. You can get same information from cones, but that's what the rods really excel at. And in very low light conditions, the cones aren't getting enough light to send a signal to the brain, so all you get is a signal from your from your rods. The cones don't get enough light. So your rods send a signal to your brain, and your brain just interprets it as black and white. So you don't see in colour when it's very, very dim light. There's not enough information from the cones. The cones are different receptors in your eye, in the retina of your eye, and they come in three sizes: small, medium, and large. And each of those has a band of frequencies of light, of colours of light, that they are sensitive to. So the large receptors are most sensitive to red. They do have a range of sensitivities, but most sensitive to red. The green receptors are most sensitive to, the medium ones are most sensitive to green. And the medium and large are very, very close together in terms of size. So some people who have colour blindness, red-green colour blindness, either their cones are too close together in their sizes, so the sensitivities are too similar, so the brain doesn't get enough information to be able to discern between red and green. Or maybe they actually only have two sizes of cones, and I don't know. There are probably lots of different types of colour blindness. Then you've got the small cones. They're most sensitive to blue light. Now, the blue cones can detect, the small cones can detect some green light as well, as the large cones can detect some green light as well. Now, there are overlaps, but your brain is very clever. So if pure red light is incident on the retina of your eye, the large cones get a lot of signal, very strong signal. The medium cones get a little bit less of a signal, and the small cones, pretty much nothing. And when your brain gets that information, your brain goes, ah, yes, that's red. Whereas if blue light is incident in your eye, the small cones get a very strong signal, the medium cones, very, very little, if any, and the large cones, very, very little, if any. And your brain goes, ah, yes, that's blue. So what's interesting is what happens when you mix certain colours together. So if I have the red and green cones, both of them sending the brain a strong signal, that can happen when true yellow light is incident in your eye. It will make the green, that's the medium, and the red, that's the large cones, both send a signal of similar strengths to the brain. So your brain goes, oh, okay, that's something new. That must be a new colour. And as a baby, you learn to call that yellow. So you can cause the same effect instead of putting true yellow into your eyes by putting the right amount of red and green. If you put the right amount of red and green incident on the receptors in your eye, on those cones, then you get the same signal levels being sent to your brain, and your brain says, when did I last see this? Oh yes, it's when I saw a banana. That was yellow. I've learnt that's yellow. So you can kind of trick the brain into seeing yellow by using green and red. That's how screens work on phones and computer monitors and TVs and all this sort of thing. That's how they work. So that's why we get yellow. So there is such a thing as yellow, true yellow, but there is also a trick that can be played on your brain by shining green and red light into your eye in the same place, or from the same place to the same part of the retina. And your brain says, when did I last see this effect? Oh, it's when I saw yellow, so I must be looking at yellow. And it's the same thing with cyan and magenta. So magenta's interesting, a really interesting one, but it's the same thing that's happening. Certain cones are sending a signal more strongly than other cones, and your brain says, when did I last see that? It kind of looks like that. All three colours, red, blue, and green, means we are exciting, we are sending a signal to all three receptors, and that happens when you've got white light, which is a range of spectrums, broad band of spectrums, a broad spectrum, should I say, of colours of light. That is what we call white light. There isn't a colour on the electromagnetic spectrum called white. The experience of seeing white light is what happens when all of our cones, all three sizes of cones, are all getting a signal at the same time. So you could argue that white doesn't exist. It's just a consequence of having all of your cones stimulated at the same time. Okay, so that's the additive mixing of colours. That's mixing light together to produce an influence that your eye understands to be certain colours. We can do the opposite. We can remove colours of light rather than adding them. And we can do that by using filters. Filters like red filters and blue filters are the two examples I've got here. So filters remove colours. If I have red, blue and green light, in other words, for all intents and purposes, what I'm saying is I have white light, which is incident upon this red filter, then the red filter will absorb blue light, and the red filter will absorb green light. But the red filter will allow the transmission of red light. So red light, knocked my drink over, so red light will be transmitted through the red filter. So here, there's only red light, because the red filter has absorbed the blue and green, leaving just red. That red light is then incident upon a blue filter. Well, the blue filter will allow the transmission of blue light, but it will absorb red and green. There's no green incident on it, so there's no green light to absorb. There's no blue incident on it, so there's no blue light to transmit. But there is red light incident, so the blue filter will absorb that red light, and over here we will have no light. So a red filter and a green filter placed together does not produce purple or magenta light. It actually prevents all light getting through. So what you're looking at will look black. Just blackness. So that is how filters work. How paint works is a sort of a mixture of different effects. You've got scattering of different colours from different pigments. So you get blue pigments and red pigments scattering light of red and blue, which your brain sees and interprets as purple. But I'm not an artist, so I'll leave that there. So these are your filters. You can get secondary colour filters as well. So you can get yellow filters. They absorb blue, but allow the transmission of red and green. And you can get cyan filters, which absorb red, but allow the transmission of blue and green. You can get magenta filters, which absorb green, but allow the transmission of blue and red. I'm just using this diagram to remember which is which. So what we're talking about when we talk about absorbing certain colours is the subtractive mixing of colours. Subtractive mixing is using filters to remove certain colours. And so that's what we've got here is three filters, three coloured filters. Red filter, sorry, not a red filter, a yellow filter, a magenta filter and a cyan filter. If white light is incident on all three filters and they're arranged like this, and the white light, when it is incident upon the yellow filter, imagine the white light is behind it and the light is coming towards you through these filters, then what would you see? Well, the yellow filter allows the transmission of green and red, so green and red your eye interprets as yellow. But if I were to place a cyan filter, which allows the transmission of green and blue, then where they cross over, the yellow filter is absorbing the blue, the cyan filter is absorbing the red, and the only colour that's not absorbed by the yellow or the cyan filter is the green. So the green is transmitted by the yellow filter, the green is transmitted by the cyan filter, so mixing those two filters together, it looks green. Do the same thing down here. The magenta filter will absorb green. The cyan filter will absorb red. But neither filter will absorb blue. So when I cross the two filters over, it looks blue. Do the same thing over here, where my cursor is there. The yellow filter absorbs blue. The cyan filter absorbs green. But neither filter absorbs red. So when I cross the filters over, it appears red. And in the middle, you've got the yellow filter absorbs blue, the cyan filter absorbs red, the magenta filter absorbs green, so red, blue and green are all absorbed, so you see no light. This is how coloured printers work. They print on white paper with yellow, cyan and magenta ink. And in doing so, by the amount of ink there absorbing different amounts of these colours, you can produce a whole spectrum of colours that are visible. So this is how printing in colours works. If you print with a colour printer on a coloured piece of paper, then you end up with colour representation which is not what was perhaps intended. Things start looking a bit wrong. This animation here, I recorded this when I got overexcited whilst looking at something my daughter was reading. She was reading a book by Roald Dahl, marvellous joke book for some reason, many years ago now. And next to her, in her bedroom, there was a light which was cycling through the primary and secondary colours. And what you could see is certain things, like right now you can't see the name of the author at the top of the book. And then, all of a sudden, wow, with this particular colour of light, the author's name becomes very, very visible. And I found that really, really fun to look at. Same with the Lego minifigures here. Certain colours will disappear. So right now, the hat looks black, the top there looks black, they all look black, they all look the same colour. But the trousers and the top of this person in the middle are completely different. You can see they're completely different. But under certain colours of light, they will look like the same colour top and bottom. And look, the hat is now a different colour to the hair, and so on. So you can see how the perception of colour depends on two things. The colour of light that is incident upon the surface, and the colours of light that the surface will reflect, compared to the colours of light the surface will absorb. So I really enjoyed that, so I took a little video of it, turned it into a GIF and stuck it in this animation many years later. Leave me alone, I like that sort of thing. Right, so there's only some other little bits of information on here, like a rainbow is a continuous spectrum of the colours of visible light. Everyone knows the colours of a rainbow: red, orange, yellow, green, blue. You might argue there's a purple, maybe. Certainly no brown or pink or whatever else they come up with in silly songs. Words that you need to know: the word opaque, light can't pass through it. The word transparent, light can pass through it and travels through in straight lines. Translucent, the light passes through it, but it scatters as it passes through it, so it produces a sort of a diffuse transmission. Also, translucent surfaces and transparent surfaces may be transparent or translucent only to certain colours. That's how filters work. And red, this is the approximate wavelength of red light. Violet, purple, this is the approximate wavelength of that purple light. And there's a rainbow. This was taken on one of our annual trips to Geneva to see the Large Hadron Collider. In my school, we go there every year, and this is the Jet d'Eau in Geneva. And you get some really beautiful pictures if you stand in the right place. Okay, let's move on to Lesson 87. Lesson 87, things are about to get much harder. So this is the topic, we're all about lenses. This lesson and the next lesson, all about lenses. So let's start with the two different types of lenses that you need to be aware of in your GCSE. If you're doing physics, if you're doing double science, then not so much. You can probably finish this video now, and it's been a pleasure having you here with me. But if you're doing physics, yeah, you'll need to know about lenses. We've got convex and concave lenses. Convex lenses bulge out, are thicker in the middle than the edge. Concave lenses bulge in, they're thinner in the middle than the edge. These are planar lenses rather than proper spherical lenses. So cylindrical lenses, these are called, rather than spherical lenses. But it's the same, you know, we can see along along a two-dimensional plane what the rays are doing. If I illuminate my convex lens with 3 parallel rays, after passing through the lens, the rays converge and cross at a certain point. So convex lenses, under certain situations, are sometimes called converging lenses. And a concave lenses, our 3 parallel rays, diverge, spread out, as though from a point, and if you were to project these lines back, it would be somewhere over here. So they are called sometimes diverging lenses. AQA doesn't tend to call them converging and diverging lenses, but the CIE IGCSE does. So it is GCSE level, so it's fine. So now you've got your idea about these two lenses. Let's just focus on the convex lens for now. The converging lens, the convex lens. We've got some parts of ray diagrams that we need to be able to label, that we need to know the technical name for. We've got a line that passes through the center of the lens, normal to the plane of the lens. So that line we call the principal axis. Sometimes it's called the optical axis, principal axis or optical axis, which passes straight through the lens. Then we've got our lens here, and what's happening? Well, if we have parallel rays, so that means, so for simplicity, let's have the rays parallel to that optical axis. They don't actually have to be, but for simplicity, let's have them that way. Then for a thin convex lens, those rays will all converge at a single point, which we call the principal focus. And the distance between the center of the lens and the principal focus is called the focal length, usually labeled on a diagram as an F. So F would be the principal focus. Now this does only work for thin lenses, because how lenses work is you get refraction from the surface at the beginning, and then you get refraction from the surface at the end. So you get two refractions. And for thick lenses, this will mean you don't actually get a single point here. It's impossible to manufacture a lens that actually has a single point as a principal focus. But the thinner the lens is, the closer to infinitesimal point for a principal focus you get. So what we tend to talk about is an ideal lens, which we call a thin lens. And on diagrams, rather than drawing the lens as a curve and showing refraction from both surfaces, what we tend to do is show the lens as a line. And so I've rotated this diagram 90 degrees now. If we drew the lens as a line, then we can have refraction from, well, not really refraction now, let's just call it a diversion of the ray from that line. So we're only dealing with one point where the ray changes direction. For convex lenses, we indicate that we are working with a convex lens by putting these arrow heads on the top and bottom of that line. If you can imagine, this looks like the edge of a lens which bulges out in the middle and bulges out in the middle. We'll look at concave lens symbols in the next part of the video. So, if I were to place an object, anything that emits light, again, it could be a primary emitter of light, like a light source, a light bulb, an LED. It could be a secondary emitter, like my face, or the tree I'm looking at out of the window. They are reflecting light, but I can consider them to be sources of light because it's a reflection, a diffuse reflection in all directions. Then there are an infinite number of rays emerging from each point on the object. So usually what we do is when we take an object, we take only one point on that object to analyze. And I'm taking the top of that object and representing the object with an arrow. There's a lot of arrows on these diagrams, which is why it can get confusing. So this arrow is the object. If you can visualize, it's like a giant road sign or something, and we're just looking at the rays that emerge from the top. There's an infinite number of rays emerging in an infinite number of directions. That's too complicated. So we are just going to take three, what we call principal rays. Three rays. And we don't actually need three. There are three principal rays. We don't actually need three because we can construct our diagram and identify the position of the image without using three rays. We can just use two, and you'll be examined on your ability to use two. There are situations where actually we can't draw the third principal ray. But let's take this first example. Three principal rays, which again we'll cover again in lesson 88 in the next part of this video. Principal ray number one we're taking one of the infinite rays, we're choosing the ray which is parallel to the principal axis, that's this dotted line going down the middle of the lens, parallel to the principal axis, and then the ray changes direction and passes through the focal point on the far side of the lens. Remember, that's how we defined the principal focus, where the focal point is, that is the principal focus, also called the focal point. We are defining that as the point where parallel rays will converge after they pass through this lens. So this ray here, which is parallel to the principal axis, will pass through that focal point. That's part of our definition of the focal point. The second ray, we are assuming that the lens is sufficiently thin. This part near the middle of the lens is pretty much flat. You know, if we imagine this principal axis like the normal, it's not normal to this part over here because the lens is at an angle compared to the normal. So it wouldn't be 90 degrees. That dotted line isn't 90 degrees to the surface of the lens over here, nor over here. But it is 90 degrees to the surface of the lens in the middle. And so if the lens is thin enough, then a ray that is passing through the very centre of the lens, it's like it's passing through a really, really thin, plain sheet of glass. So it doesn't really change direction. So this second principal ray passes through the centre of the lens undeflected. And you'll notice that the first principal ray and the second principal ray cross at this point here. So if I were sat over here looking, maybe I had one eye along that ray and one eye along that ray, then my brain would say that the rays are coming from here. That's the point from which the rays appear to be diverging. But more than that, the rays appear to be coming from here, and they are actually passing through that point. So we call that a real image. The third principal ray makes use of an idea called the reversibility of rays. If a parallel ray, parallel to the principal axis, incident upon the centre of the lens, passes through the focal point on the far side of the lens, then a ray travelling in exactly the opposite direction, parallel to the principal axis, would travel through the near focal point. And if a ray would travel in that direction along that path, then a ray going in exactly the opposite direction would follow exactly the same path in reverse. Now, on your ray diagrams, I haven't drawn them on these, but you really must draw arrows to indicate the direction of the rays. You must draw those arrows. Don't go crazy and make them look like feathers by drawing too many arrows, but just draw a few arrows so that it's clear that the light is travelling in this direction. Because if I were able to somehow construct a system with 3 laser beams pointing in the completely opposite direction, then I would produce an image over here. That's how light works. It follows the same path in both directions. So those are the 3 principal rays. Now you can see if I place the object on the focal point, on the near focal point, I say near because it's near to the object, I've got a problem here because the third principal ray, which passes through the object is this point up here, the ray that passes through there cannot pass through the focal point and then pass through the lens. It can't. That's impossible. Parallel to the plane of the lens, so there's no way it's going to pass through the lens. So I can only draw the first and the second principal ray. And those rays will be parallel after they pass through the lens. Therefore, I do not get an image. There is no image formed. This is just the example of parallel rays. If you imagine the rays were travelling in the opposite direction, those parallel rays would focus to a point which is the distance from the middle of the lens of 1 focal length. So it's just the definition of the principal focus again, in reverse, but now we've moved the rays so that they're no longer parallel to the principal axis and thus moved the principal focus all the way up, well, the focal point all the way up here, but it's still the same distance away from the lens. But we're looking at it in the forward direction, so we draw our arrows for the rays like this, and we have no image formed. Weirder still is what happens when the object, and this is only for convex lenses, when the object is closer to the lens than one focal length. Now in that case, if we draw our first two principal rays, the first one passes parallel to the principal axis and then through the far focal point. The second one passes straight through the centre of the lens undeflected. And if I were to place an eye on that ray and an eye on this ray, apparently my pupil's outside my eye there we go, then what would I see? Well, the rays are diverging, but that means they're diverging from a point, just like the rays here at the top were diverging from a point. The difference is, in the first example, that point is where the light actually does pass through it, so it's a real image. In this last case here, the point is all the way back here. Just like we did with the lens, with the mirror, if we project those lines back, we find the point from which the rays appear to diverge. But the light didn't actually pass through that point. So this is a virtual image. And you'll notice that your convex lens has produced an image larger than the object. That is not the case when I place the object farther from the lens than the focal point. That produces an image which is smaller than the object. And you can, if you've ever got a lens and played around with this and moved it around relative to an object, you'll see exactly this effect happen. If the object is too far away from the lens, the image is closer to you than the lens, and yet it is smaller than the object. If you push the lens down so it's closer to the object, close enough to the object, then you will see that the image becomes larger and appears to be further away from us than the object, making it easier for our eyes to focus on. This is how magnifying glasses work. So those are the three diagrams which show the application of the same two principal rays, the first and second, to these situations where the object is farther from the lens than the focal length. The object is the distance from the lens equal to the focal length, and the object is closer to the lens than one focal length. There's three different situations. If the object is twice the distance from the lens than one focal length, then the real image is exactly the same size as the object. That's just an interesting one to know. If the distance to the object, sometimes we call that u, is equal to 2f, then the image size is equal to the object size. If the image is inverted, we actually say that's a positive image size, and if the image is not inverted, as is the case with this virtual image, we actually say that is a negative image size, which is a little bit interesting, but it is what it is. Don't worry about that for your 𝗟𝗀𝘀𝘀𝘀 GCSE though. So the inversion of the image, you can see here a little doodle that shows ray emerging from the top of a person and from the bottom of a person, causing the image to be inverted. That's only if the object is farther from the lens than one focal length. And I did mention that the image could be smaller, the same size, or larger than the object. Well, we can calculate a magnification of the lens by measuring the height of the image. So in this case, it would be this height, there, measuring that with a ruler. Measuring the height of the object, so that would be this height here, measuring that with a ruler. And the image height divided by the object height, what's that? I mean, that one there looks like it's more than 2. The image height is more than twice as high as the object. There's no units to this, because the unit of the image height and the unit of the object height, if they're the same, the units cancel. So this would be a magnification of maybe 2.2, 2.3. I haven't measured it. You can measure it yourself later. That would be that magnification. Whereas this magnification is what? 0.7, maybe 0.6? I don't know. I haven't measured them. Technically, this would be negative 2.2 or 2.3 or whatever it is. This would be positive. But don't worry about the sign. You really don't need to worry about that. So that's the introduction to lenses. Yeah, that's the introduction. And you do need to learn those principal rays, because you'll have to be able to construct these diagrams. So lesson 88, we're going to just re-emphasize those convex lens rules. The first ray, the first principal ray, parallel to the principal axis, passing through the focal point after the lens. That's this ray. Let's get my pen out. Yeah, that's this ray here. Second principal ray, let's label that 1. Second principal ray passes through the centre of the lens undeflected. Let's label that 2. And the third principal ray, if you can draw it, does this. There are ways of drawing the third principal ray even when the object is closer to the lens than one focal length. It is possible to draw the third principal ray, but it takes quite a bit of thought, and it's not an easy thing to explain. So if we don't need it for GCSE, let's just leave it. Leave it for A-level. Although lenses don't come up in the AQA A-level, unless you're doing astronomy. Then we've got, or maybe medical physics as well. I'm not sure about medical physics. I can't remember. It's been about over a decade since I taught that course. Right, so anyway, that's convex lenses. Convex lenses. And we've got some stuff down here about when we get real images, virtual images, and the size of the image. So magnification less than 1, that means its image is smaller than the object when the distance is greater than twice the focal length. You can read that. That's stuff I've already talked about in the previous lesson earlier in this video. So what about a concave lens? Well, they are divergent lenses. Diverging lenses. So the lenses diverge, the rays diverge from a point. The principal rays here are kind of similar to the convex ones, but all inside out. So the first principal ray, parallel to the principal axis, is how it starts. That sounds familiar. But then rather than converging towards the far focal point, it diverges away from the near focal point. In order to know where it diverges, you need to draw a dotted line, a construction line, between the focal point and the point where your first part of the first principal ray is incident upon that centre of the lens. Notice the lens has a different symbol, different arrows on the edges to indicate that it is a concave lens. Okay, wider at the edge, thinner in the middle. Convex lens symbol, concave lens symbol. Do learn those. Now, if I place my eye here, I will think that the image, or I will see the image somewhere along this line. I don't know where, but it'll be somewhere along that line. The second principal ray, I'm going to draw it as this one here, which is exactly the same as it was for a convex lens. The ray passes through the centre of the lens undeflected. It only works for thin lenses. Now, if that's the case, and I place my eye here, I think the image is somewhere along this line. And the place where those two agree is here, so that is the position of our image. The top of this thing, the image, is a virtual image because ray 1 doesn't actually pass through that point, so it's a virtual image. You can project a real image on a screen. If I were to place a screen here and then look at it from over here, oh, that's not a very good one. I'm not actually looking at it. Looking at it from over here, then I would see the image on that screen. If it's a matte screen, so I get a diffuse reflection, I would see the image. That's how projector screens work. If I look at the case of a concave lens and a virtual image, if I were to place a screen here, all I'm doing is blocking the light, so I can't see anything. So you cannot see, you cannot project the image, a virtual image, onto a screen. But you can project a real image onto a screen. It's one of the differences between real images and virtual images. The third principal ray, I've included it on the diagram, but I haven't included it in the notes up here. It's like how we had for the convex lens, where it's just the same as the first principal ray, but all in reverse. But it's harder to see because with the first principal ray for concave lenses, we were parallel to the principal axis at the start, and then diverge away from the near focal point. With this one, we go towards the far focal point and then parallel to the principal axis after the lens. And then if you were to look down the ray, you would see the point where the ray appears to come from. So if you have 3 eyes, you'd see that. Or you could move your head, perhaps, and you'd see that. Don't worry about the third principal ray, though, because you're only going to be examined on the first 2. There are 3. You're only going to be examined on the first 2. So that is ray diagrams. Now, ray diagrams will take a lot of time to master. You will have to practice drawing them, and you can get a lot of practice drawing them using Isaac Physics. There are a lot of questions on Isaac Physics where you have to draw ray diagrams of lenses in order to measure and calculate magnifications. And there are even questions involving the lens equations for when you measure the distance to the object, distance to the image, focal length. Well, any two of those you can use to calculate the third. I'm not going to go into that because I'm really focusing on the GCSE, not the IGCSE here. If you're interested in that, you can go and have a look on Isaac Physics, and there's some good stuff on there all about lenses. So that's the end of this video about light. Hope it's been useful. Don't forget, weekly tuition during term time. Sign up on physicswithkeith.com if you're interested. It's not like this. It's interactive. It's not a series of lectures that you sign up for. You sign up for tuition. It's very different. Yeah, if you're interested, there's the QR code. Off you go. Right, thank you very much for tuning in. Hope it's been useful. Take care, and I'll see you in the penultimate video, all about electromagnetism. Bye-bye.